So, welcome back. We just looked at best first search and hill climbing. We found that best first search is a complete algorithm which will find a solution, but it requires exponential amount of time and space typically. Then we looked at local search algorithm, which is hill climbing, which simply follows the gradient, and we saw that it is computationally efficient. The only problem is that it does not always find the solution essentially. It gets stuck in local optima essentially, whether it's if it's a maximization problem and a local maximum, otherwise in a local minimum. So, let us look at some approaches to get around this problem of getting stuck in a local optima or optimum using hill climbing. So, this is a recap. It is a constant space algorithm. It only looks at its neighbors. It moves to a better node. If it cannot, then it terminates. So, time complexity is also good. Its termination criteria is different. It stops when it has reached what it thinks is the optimum. However, that may not be the global optimum that we are interested in essentially. So, we want to see how to escape from this local optimum that hill climbing can get stuck in, and how to move towards a global optimum. So, we had seen this with the 8 puzzle example, that hill climbing would have got stuck at this local minimum. And we said that we need algorithms that can do better than hill climbing, and we will look at these 3 deterministic algorithms next. We also define this notion of solution space or plan space search to begin with. So, what do we mean by solution space search? By solution space search, we mean a formulation of the search problem such that when we find the goal node, we have the solution and we are done essentially. We do not have to reconstruct the path essentially. Configuration problems obviously fall easily into this category. Every node in the search space is a candidate solution, and a candidate is a solution if it satisfies the goal description. But we will see later that planning problems can also be solved in the solution space, and then we say that we are solving them in the plan space. Every node is a candidate plan, and these algorithms are known as plan space planning. So, we need to observe the difference between synthesis and perturbation. Synthesis methods are constructive methods, and starting with the initial state, we build the solution piece by piece. So, for example, if you were doing the n queens problem, then we would place the first queen on the board, then we would see where to place the second queen. We would try different options if you are doing that first search, and eventually find a position for that, and then look for a position for the third queen and the fourth queen and so on essentially. On the other hand, look at the following representation. We have an index which represents the row number on the board, and we have values for those indexes which are the column numbers for on that board essentially. So, when we say that the first element in this list is A, we mean that the first queen or the queen in the first row is in column A, as you can see, which is on the diagram on this thing. Then when the queen in the second row is in column C as shown here, and the rest of the thing says that the third queen is in column E, the fourth is in B and F and D and so on essentially. So, this is a representation of the n queens problem as a one dimensional array, where implicitly the first element is the queen in the first row, the second element is the queen in the second row and so on, and what we have stated is the column in which the queen exists. Now, if we take permutations of this representation of this one dimensional array, then we would end up generating new candidates. So, this is what we mean by perturbation, that we take a candidate solution. So, for example, A, C, E, B, F, D, it may not be a solution, but it is definitely a candidate solution. So, what is it saying? It is saying that the third queen is on E, which is here, the fourth queen is on B, which is here, the fifth queen is on F, which is here, and the sixth queen is on D, which is here. So, this is not a solution obviously, because you can see that these two queens are attacking each other essentially. But nevertheless, it is a candidate solution, and if we did some amount of perturbation, either taking shuffling the array or something like that, then we would generate new candidate solutions, and that is the idea of perturbation. So, let us come back to the SAT problem. Given a Boolean formula made up of a set of propositional variables, each of which can be true or false or 1 on 0, to find an assignment for the variable such that the given formula evaluates to true or to 1 essentially. So, for example, here is a formula written in propositional logic or Boolean this thing, can be made true by giving these values: A is equal to true, C is equal to true, D is equal to false, and E is equal to false, and there may be other valuations also. Very often SAT problems are studied in conjunctive normal form or CNF. So, the above formula is not in CNF because it has things, for example, the implication sign and so on, but in the CNF form the main connective is an and inside every clause, as this is called. So, this is called a clause. We have only a disjunction or a negation sign essentially. So, essentially we can say so many clauses are there in the formula. So, let us see how solution space and search and perturbative methods can be combined. The solution space is a space of candidate solutions. Search method generates neighbors of a candidate by applying some perturbation to a given candidate. So, that is a move gen function, and in some communities we also call them as a neighborhood function. So, a SAT problem with n variables has 2 raised to n candidates, because there are n variables, each variable can be either true or false or 1 or 0. So, there are 2 raised to n possible candidates, where each candidate is a n bit string, because if there are n variables then there are n bits essentially. So, when n is equal to 7, for example, as shown here, a neighborhood function, we could choose a neighborhood function or perturbation function which changes only 1 bit essentially. So, these are all the neighbors for this particular candidate, where the bit that is changed is shown in red essentially. So, a search algorithm would navigate this space. This space is a solution space where every node is a candidate solution, and of course, we can evaluate whether it is a goal node or not essentially. The other problem that we would be of interested in is the travelling salesperson problem or the travelling salesman problem, which is considered by many to be the holy grail of computer science. So, this is how the problem is defined, that given a set of cities and given a distance measure between every pair of cities, remember every pair of cities, the task is to find a Hamiltonian cycle, visit each city exactly once, and in addition we have a constraint that we want a tour with the least cost in the travelling salesman problem. When the underlying graph is not complete, for example, in the real world, not every, let us say these are flights, not every city has a flight to every other city. So, we will assume that we can connect them, we can connect the missing edges, we can add the missing edges, and with a very high cost essentially. And the basic idea is to maintain the fact that any permutation of cities, and by permutation here we would mean the order in which you are going to visit the cities, is going to be a possible candidate. So, you can say that you can go from this city to this city also, even though there is no edge between that. There may not be an edge between that or something like that. Now, this TSP is a much harder problem than SAT, and it falls into the category of being an NP hard problem, which means that it needs at least exponential time. And what is more is that when you are looking at a candidate SAT solution, you can look at the candidate and decide whether it is a solution or not. When you look at a candidate TSP solution, you can of course decide whether it is a tour or not, but you cannot decide whether it is the optimal tour or not. So, in that sense it is a much harder problem than SAT essentially. Now, if you go to this website TSP lib, they have a collection of problems which they have got together from various sources, and some of them are like real world problems. How can we solve the TSP? So, first let us look at a greedy constructive methods. The simplest is the nearest neighbor heuristic. It says that start at some city and move to the nearest neighbor, as long as it does not close the loop prematurely. We will see this in a moment. This is a greedy approach. You start at some city and move to the nearest neighbor. As you can see, it will not work with this problem. So, for example, if I were to start with this, then I would go around like this, and then I would probably go here, and then I would probably go there, and then I would probably come here essentially. Now, clearly not the optimal tour essentially. So, it is a NP hard problem. So, it is not easy to find optimal tours, especially it is not easy to find tours using greedy methods. Even for problems which have additional constraints. So, for example, one of the constraints that we may want to add to TSP is that the distance metric, the distance measure is a metric essentially, which means it satisfies the triangle inequality and so on. And for such problems, it is typically not so hard to find problems, but in the general case, it is a hard problem. A variation of nearest neighbor would be to extend the partial tour at either end essentially. Why just go in one direction? You could go in both the ends. Another approach is called the greedy heuristic, and it works like this. It is a little bit like Kruskal's algorithm for finding the minimum spanning tree. You sort the edges, add the shortest available edge to the tour, and you keep doing that as long as you are not making smaller loops essentially. So, here is a nearest neighbor approach, just to get a feel of what it does. You start at some city and move to the nearest neighbor, as long as you are not closing the loop. So, let us say we choose this as a starting city, and essentially we go at every step to the nearest neighbor, and we will see that this is a kind of tour that would be constructed. Clearly, it is not optimal again. For example, for visiting this city, it would have been better if you had come here and then gone from here to here, and things like that essentially. But it is a greedy approach, and it can sometimes give you reasonably good tours essentially. The algorithm known as the greedy heuristic says that add the smallest edges first. So, for the same problem, here is a snapshot of what are the edges that you might have added before you continue from there. So, from there we will look at the next smallest edge. We can't add this edge because that would close a loop there, but we can't add this edge also, because you can visit because that would mean that one particular city is visited more than once. So, one of the properties of a TSP tour is that every city has one incoming edge and one outgoing edge. So, you can't have 3 edges onto a city, but you could have added this edge next, and maybe you could have added this edge next, and so on and so forth. You keep adding the smallest possible edges, and till you have some sort of a solution. Maybe you should try it out, try to complete and see what will happen with this particular problem instance. There is another approach called the savings heuristic, which is quite popular, and the way it works is as follows, that you start with n minus tours of length 2 anchored on some base vertex, and then you perform n minus 2 merge operations to construct the tour. What is a merge operation? You remove two edges connected to the base vertex from two loops and add the edge to connect the two hanging vertices essentially. Which two? The two edges are chosen such that there is maximum savings of total cost in the resulting graph. That is why it has got this name savings heuristic. So, here is an example. You start with this constructing this. So, there are 5 cities in this. So, you can see that there are 4 tours of n minus 1, 4 tours of length 2 essentially, starting with the anchored city, which is the red city. So, every red city is connected to every other city, and that forms a small loop. Then we remove these 2 red edges and connect those hanging edges with a new one. Then we remove these 2 red edges again and connect the hanging cities, and in the last step we remove these 2 red edges and connect the remaining hanging cities, and what we have is a tour essentially. So, just to illustrate how the savings heuristic works, it is a very popular heuristic used for solving TSP. So, this is something which I had downloaded from this website, but at the moment I could not find this link again. So, anyway, so this is a sample run created by these algorithms, the greedy tour, the nearest neighbor tour, the savings tour, and also we have the optimal tour essentially. So, you can compare how the different greedy approaches perform with respect to the optimal tour. You can see that the greedy tour and the nearest neighbor tour has lot of long lines thrown here and there, like for example, in the example that we saw earlier, and the saving tours seems to be performing a little bit better. It may or may not be optimal. So, now let us look at perturbation operator. We have looked at greedy constructive approaches for constructing tours. Now, let us look and see that if you are working in the solution space where you are given some tour, how can you perturb that to produce new tours. So, one of the simplest operators is called the two city exchange, where the two shaded cities that we have seen. So, assuming that the original tour was going from left to right, and there are some edges which I have not drawn. So, they would have been here and here and here and here. But if we exchange these two shaded cities, then what do we mean by exchange? We are saying that instead of going from this x to this y, you do not do this. Instead, you go to the other city that you are exchanging. Instead of going to this city which we have called y, go to this city called which we have called z. So, we have exchanged y and z essentially, and we have changed the tour. So, if this was a starting tour and these are the two cities that we were exchanging, then this is how the tour would look after we have exchanged the two cities. What do we mean by exchange? Because we are assuming that the tour is represented by what is called as a path representation, where it is a sequence of cities going from city 1 to city 2 to city 3 and so on essentially. So, and we are simply changing the order essentially. The two cities can be selected in NC two ways obviously. So, that would be the neighborhood function. Sometimes people prefer edge exchange instead of city exchange. Why is that? Because it is edge which contributes to the cost of the tour, and uh, maybe if you are using edge exchanges, then you can try to remove longer edges essentially. So, we have removed this edge and we have added this edge and this edge. Yeah. So, we have got a new tour. Again, edges can be selected in NC two ways. 3 edge exchange says that remove 3 edges from the tour, some 3 edges, maybe some 3 long edges that you do not like, and replace them with some other edges, so that we have a tour. So, what you see on the left is that we have removed 3 edges. So, we have broken the tour into 3 separate components. So, we want to reconstruct the tour, and this can be done in 4 different ways, as can be seen here, and those would be the neighbors essentially. So, the 3 edges themselves can be selected in NC 3 ways. So, you can see that these are different neighborhood functions. What is the state space? The state space in a travelling salesman problem is all permutations of all the n cities, and what the neighborhood function does is connect some candidate tours to some other candidate tours, and these are the 2 different kinds of things we typically do: city exchange or edge exchange. Let us talk a little bit about complexity. Both SAT and TSP problems are hard problems. We have already said that. Both have huge search spaces, and hence we are looking for local search methods. SAT is NP complete. In fact, it was the problem that was used to define the NP complete set by Gary and Johnson. It requires exponential time to solve, but can be verified in polynomial time. As I said earlier, TSP is NP hard. It requires factorial time to solve, because you are choosing different permutations of cities. The first city you can choose in n ways, the second city you can choose in n-1 ways, and so on. And moreover, it cannot be verified easily, because you may construct a tour, but how do you know whether it is an optimal tour or not essentially. So, this gives you a feel of exploding search spaces. So, the number of candidates in SAT is 2 raised to n, and this basically shows that if n is equal to 1, there are 2 candidates, if n equal to 2, there are 4 candidates, and so on and so forth. As you go to 100, n is equal to 100, then we have something like 10 raised to 30 candidates, which is a huge number of, the space is huge essentially. So, if we have a 100 variable SAT, then this is how the space would look like. TSP is even worse. Initially, of course, if there is one city, then there is only one tour, there is no tour in fact. If there are 2 cities, then you can think of 2 tours essentially. In fact, actually you can think of only one tour if there are 2 cities. What I have written here is n factorial. N factorial of 2 is 2 essentially. But in practice, if I choose this as a first city and if I choose the other one as a first city, so let us say this is P and this is Q. So, the tour PQ is equal to the QP essentially. Because it is just a sense, it is the direction that you are changing essentially. So, in general, if there are n cities, then you can rotate them and you can reverse them, and they would represent the same tour. But we have not written that, we have just mentioned here n factorial. So, in practice, it should be n minus 1 factorial divided by 2. This 2 comes because of the fact that the reverse of a string is the same tour essentially. In any case, the point is that they tend to grow as a factorial, and the factorial function you should study grows much more rapidly than the exponential function. So, for n is equal to 8, for example, there are only 256 candidates, but in the factorial function there are already 40,000 candidates essentially. And as you can see, with n is equal to 50, it goes to 10 raised to 64, and then for n raised to 100, 10 raised to 157. The last column shows the ratio between the state space of TSP versus SAT, and you can see that for n equal to 100, it is 10 raised to 127 times more than the SAT state space. So, these are basically huge problems, and we cannot afford to solve them by using brute force methods. We can't look at every candidate and say whether it's a solution or not, and that's why we are looking at local search methods essentially. How much time would you need to solve SAT? Of course, you may strike the solution quickly. In the SAT, your first guess may be a good guess or so on, but in the worst case, how much time do you need? If there is a 50 variable SAT problem, then 2 raised to n is this number which is given here, and you can see that what I have done is you are saying that if a million nodes in a second, that means we just chop off those 6 smallest significant bits there, and whatever remains is the number of seconds that you will get. Then I have assumed that there are 100 seconds to a minute, so I have chopped off those 206, then 100 minutes to an hour, so chopped off this 99, then 100 hours in a day, chopped off this 89, so you have 1125 days, and assuming 1000 days in a year, so that leaves you this 1.1. For 100 cities, it is quite different, and we are talking about a SAT problem here. So, we started with 10 raised to 30, and we have reduced it to 10 raised to 24, because we are doing a million nodes a second, and then we gradually keep removing that many zeros, 2 zeros, 2 zeros, and so on, and eventually you will see that it is a large number of centuries that you need to solve a 100 variable SAT problem, and we are not even talking about TSP here essentially. So, clearly brute force is not going to work, and what we need to do is to look at some approaches which will be local search methods, but which will not get stuck on local optima essentially. So, we will do that next. We will start by searching in the solution space or in the plan space essentially.